In this slide, on my uh, PowerPoint is slide number 16. This illustrates a little bit more about how to visualize or understand acceleration. So basically, we're doing is looking at the rate at which a ball drops off of of a high elevation. We again assume that there is no air resistance to the ball. And as we know from Galileo's experiment, that it really does not matter what the weight or or the mass of the object is. And we'll talk about difference between mass and weight a little bit later, but for now we will assume that as one increases, the other one does too. So in this case right here, we drop a ball from a high point, and what the acceleration of 10 meters per second tells us is that if we drop the ball from rest, that is to say, we don't give it any velocity down when we let go of it, then after 1 second, it will achieve a velocity of 10 meters per second. After 2 seconds, it will achieve a velocity of 20 meters per second. And after 3 seconds, it will achieve a velocity of 30 meters per second, and so on. So this is the way to visualize or understand the acceleration of gravity. Now, bear in mind that we have used the approximation. Then instead of using 9.8 meters per second, we are using 10 meters per second, just so that we can do crude calculations more quickly, and it becomes easier uh, to avoid doing more complicated calculations. Um, the next slide is going to allow you to um, work a problem, and then you can see for yourself if you're able to get the correct answer. In this slide, on my uh, PowerPoint is slide number 16. This illustrates a little bit more about how to visualize or understand acceleration. So basically, we're doing is looking at the rate at which a ball drops off of of a high elevation. We again assume that there is no air resistance to the ball. And as we know from Galileo's experiment, that it really does not matter what the weight or or the mass of the object is. And we'll talk about difference between mass and weight a little bit later, but for now we will assume that as one increases, the other one does too. So in this case right here, we drop a ball from a high point, and what the acceleration of 10 meters per second tells us is that if we drop the ball from rest, that is to say, we don't give it any velocity down when we let go of it, then after 1 second, it will achieve a velocity of 10 meters per second. After 2 seconds, it will achieve a velocity of 20 meters per second. And after 3 seconds, it will achieve a velocity of 30 meters per second, and so on. So this is the way to visualize or understand the acceleration of gravity. Now, bear in mind that we have used the approximation. then instead of using 9.8 meters per second, we are using 10 meters per second, just so that we can do crude calculations more quickly, and it becomes easier uh, to avoid doing more complicated calculations. Um, the next slide is going to allow you to um, work a problem, and then you can see for yourself if you're able to get the correct answer. Now, in the previous slides, we asked the question, how does the velocity of a free-falling object change with time? And there was a fairly simple calculation for that, and we simply multiply the nominal value of 10 meters per second times the time, and that tells us what the velocity will be at any given time. Now, in this slide, we're looking at a slightly different quantity of interest, which is how far did the object fall when after a certain time from when it's released. And that equation is given by what you see here. It is distance equals 1/2 acceleration times the time since the dropping of the ball squared. So in this case, for example, when we drop the ball, we want to say how far did it fall after 1 second. So 1/2 acceleration is 5. 1 second squared is 1. So 1 times 5 is 5, and the distance is 5 meters. Similarly, working through the other examples, you can find that after 2 seconds it falls 20 meters, and after 3 seconds it falls 45 meters. So the rate at which the distance between adjacent seconds of time, the distance it falls, is increasing after every second. So if you were to go back and look at slide 16, we're now looking at what is the distance that the object reached after 1 second, after 2 seconds, and after 3 seconds. And you see those three dots. And those dots in this calculation would show that the object after 1 second, which is the first dot, would have fallen 5 meters. The distance it's falling after the second is the total distance it would have traveled is 20, and after 3 seconds, the total distance it would have fallen is 45, assuming, of course, it hasn't hit the ground yet. In this slide, you are asked to calculate how far a falling object will have traveled after it has been falling for 4 seconds. And so I'm going to let you do this calculation and resume on the following slide after you check your answer. Now, in this slide, we look a little more detail of how velocities are added vectorially when there is more than one velocity vector involved with a given problem. So in this problem, what you see is that we suppose that we have an airplane that is able to fly at a speed of 80 kilometers per hour in still air. It means, in other words, there's no air motion above the ground, commonly known as still air. But now we consider a case where that same airplane is placed in a crosswind of 60 kilometers per hour. And as you would expect, the pushing of the air against the plane is going to give it a component that is no longer just in the northern direction, but also in this case in the easterly direction as well. So the way that we find out what is the velocity or the speed of the airplane over the ground, um, as well as the angle, is to do a vectorial addition of velocities. So we add two velocities together. One is the velocity of the airplane in still air. That's the vertical vector that reaches up um, at about, as shown here, is 80 kilometers per hour. Now, if you're doing this on a piece of graph paper, for example, you might choose to write this down as a scale and say, for example, that for every inch of a vector corresponds to 40 kilometers per hour. So in this case, the length of the vector would be 2 inches because it is twice that, or 80 kilometers per hour. That would be the first vector that you draw on the paper, and it points true north. Now what you do is to add a second vector, which is the crosswind. So this is the effect of the velocity of the wind pushing on the plane, and it is going to cause it to take a northeasterly direction as a result. And the way we find the net speed or velocity over ground is to add these two vectors vectorially. So we add the velocity of the airplane in a still air, which is the vertical vector, and then we add also a horizontal vector, which is whose length is represented by the speed of the wind. So in our example that we just talked about, if, for example, on a piece of graph paper, 1 inch represents 40 kilometers per hour, I would draw another arrow of length 1.5 inches horizontally, and I would place the tail of that vector at the head of the airplane's vector, and I would draw it horizontally since it's a crosswind. It's a we call it a westerly wind since it's coming from the west, and then that goes a vector blowing the plane to the east. Therefore, when we add those two vectors together, we get the addition. We draw uh, the length of the resultant vector is a line segment that starts where you see in the lower left and goes up to where the tip of the crosswind arrow would be, and that places us at the at the resultant point, which is shows that the airplane is taking a trajectory to the northeasterly direction. So we can we are asked in this case is to find out what is the angle of that velocity over the ground, or one way of saying it is if 0 degrees is true north and 90 degrees is true east, what is the angle that the airplane actually makes it over the ground? So that's your question to answer. And if I you think about this a little bit, but basically what you can see or what you should know is that if the length of the wind vector, the crosswind, is shorter than the length of the 80 kilometers per hour, then the angle is going to be less than 45 degrees. And if the crosswind is greater than 60 kilometers per hour, then, I'm sorry, greater than 80, which is the airplane speed, then the resultant vector will have an angle greater than 45 degrees from true north. So this allows us then to add velocity vectors. I can find two things from this. What is the direction over the ground, which in this case is less than 45 degrees. And I can also find out what the speed of the airplane is over the ground by using the Pythagorean rule that the sum of the squares of two sides of a right triangle is equal to the square of the hypotenuse. So if I take 60 squared, for example, and add 80 squared, and then take the square root of that, I get 100 kilometers per hour. In this problem, you are asked to find what is the angle of raindrops that would be falling on you or the object that you're driving in, if it's a car or a motorcycle, um, as seen by you. So let's take a case where we are in a slow moving motorcycle at 4 meters per second. And we'll assume that the raindrops are coming down at also at a velocity of 4 meters per second. Then you're asked to find out that relative to you, what is the angle that the raindrops are hitting your face or your windshield. So the object of the question here is to be able to add velocity vectors, and you take your speed at 4 meters per second. I add to that vectorially a wind speed of 4 meters per second. And what I look for is the resultant of adding those two vectors together. And when I do that, I find that I have a 45-degree right triangle, a right triangle consisting of two 45 degrees and a 90. So because the 90 degrees is because the rain is falling vertically, and the object, which is myself or the car or the motorcycle, is traveling also at 4 meters per second. So adding those two vectors together, I get a similar case as we did with the airplane, with a vectorial sum being the hypotenuse of a right triangle. In this case, since um, the sides of the right triangle are 4 meters per second on each side, and again, drawing vectors on a piece of paper, I have to develop what I would call a scale, which might be, for example, I'm going to let 4 meters per second equals 1 inch drawn out on the paper. Then I have a vector which is 1 inch horizontally, representing my motion, and I add to that 4 meters vertically with another vector, and the resultant vector I draw the connecting the origin, the tail of the first vector to the head of the second vector, and I get a right triangle with two equal sides, each 1 inch long. Therefore, it is a 45-degree and 45-degree and 90 degrees in my triangle, and therefore the angle that the drops are hitting the windshield occur at 45 degrees. Now, for the last four slides of this chapter, I'm going to let you read them and do a self-check answering on the question presented and a quick review of speed and velocity. I think you'll find these relatively easy, and then you should be ready to start your homework assignment for Chapter 3.